Here is the problem. Let I and J be two sets, and F from I Cartesian product J to G a mapping into a commutative monoid which takes the value E for almost all pairs ij. Show that the following equation is true. First of all, let us clarify the meaning of a commutative monoid. Combining the definition we previously have in the first algebra video, our normal understanding of commutativity, which basically means the order of the law of composition does not matter, and the target of F, a commutative monoid specifically means the set G with a law of composition that is commutative and associative and have a unit element E. Secondly, the phrase almost all in algebra means all but a finite number of. In other words, except a finite number of elements, the statement holds true. With the above setup, here is my solution. Since only a finite number of pairs ij produce values other than E through the map F, I can limit the product from the whole set I Cartesian product J to just a finite number of i's and j set involved in producing non-trivial results. We can imagine the set I Cartesian product J as a two-dimensional plane with only finite number of points on it. This implies that there exists finite number of i's and j's to mark each point. Although the intersections cover more than the necessary points, the rest will produce the unit element E and does not affect the result. Therefore, I can expand the product and arrange them as a block. Each row represents the product of all j's with a fixed I. Then because of both the property of commutativity and associativity, we can rearrange a way similar to a transpose in matrix notation, which each row now represents the product of all i's with a fixed j. This is equivalent to first product all the possible i's with a fixed j, then product such results with all possible j's. Finally, include back all of the other pairs ij, then we successfully show that this equation is true.